Welcome to DWBI Adda channel. Please subscribe for latest training videos.
Hello, welcome to the session on simple linear regression using Python. Simple linear regression is the one where we try to predict the value of a dependent variable based on one independent variable. Let's try to take an example and understand the things. This is the dataset we will be working on. This dataset talks about the number of minutes a technician took to fix certain number of computers. For example, at one instance, he took 49 minutes to fix 3 computers, 64 minutes for 4 computers, and in other instance, he took 74 minutes for 4 computers. Based on this data, we would like to predict the number of minutes he would take to fix certain number of computers. Let's look at the code. First, I would like to import all the necessary packages. For example, I need pandas and the numpy to work on data frames and scientific computations respectively. Seaborn and Matplotlib are used for plotting purposes. The SciPy and the scikit-learn linear model is used for the machine learning purpose. Alright, so let's import the data file into a data frame. So computers is a data frame which I made over here. I do a read.csv and I read the file and save it in the data frame. I do a computers.head to understand the data. I see the first 5 records getting printed. I'm happy with that. I have 2 columns, units and minutes, and these are the data. Now, let's try to separate the data. The one will be the independent variable and the other will be the dependent variable. So dependent variable in my case is minutes. I save it in minutes, and the independent variable in my case is units, and I save it in units. After this, I would try to run the linear regression model on this. In order to do that, I would first create an object model out of the linear regression package and then do a model.fit. Let's remember model.fit takes 2 parameters. One is the x-axis and the other is the y-axis. Y is always the dependent variable and x is always the independent variable. In my case, units goes to x and minutes goes to y. I do a model.fit that generates the linear regression model and saves it in model. Now I would like to understand what my model has predicted. To do that, I would do model.intercept first and then model.coefficient. This would give me the intercept and the coefficient for the given model, which means it gives me the intercept and the coefficient for the best fit line for this model. In other words, my model, my simple linear regression model says that the best fit line for the given data set is nothing but y equal to 4.16 plus 15.50 times x, which is nothing but the intercept and the coefficient rounded off to 2 decimal places. So this is what my simple linear regression model is. But we all know there is no model which predicts 100% correct. There has to be an error in every model. So we need to find out how good our model is. So let's take some parameters to evaluate our model and try to understand how good my model is doing. There are certain ways to evaluate a model. To do that, let's first try to predict the values of the given units which I already have in my dataset and try to make a prediction for the same units, and let's make a comparison of the predicted values with the actual values. Alright, to do that, my first step would be I create a y underscore predicted and save it in my save the output of my model in y underscore predicted. I can do that by model.predict. I pass the independent variable to that, which is my units, and save it in my dependent variable, which is y underscore predicted. I do a y predicted dot shape. It gives me 14, 1. I'm good with that because I know there are 14 records in my data set. Alright. Now, the minutes, which I got it from the actual data frame, is nothing but the actual minutes. I save it as y underscore actual to follow a standard naming convention. I do a y actual dot shape 14.1. Again, I'm happy with that. I know there are 14 records. Let's try to see what is the type of y predicted. When I do a type of y predicted, it gives me a numpy array. So any prediction which is happening from a model is usually of the data type numpy array. Alright, now let's get into the actual comparison of my model against the actual data. Okay, so I do a graph over here to have a better understanding. I know there are 14 records, so I just took an index of 1 to 15. This will be my x-axis, and in my y-axis, I plot two lines. In the y-axis will be the minutes, and one line is in blue and the other is in red. The predicted goes to red, and the actual goes to blue. This gives me a holistic view of my prediction. We can clearly see here my predicted values overlap considerably with the actual values, which means they are pretty close to the actual values. This gives me a hint that my model is probably doing good over here. At the same time, I would like to introduce a term called overfitting. At the same time, I have the fear that my data could be overfitting. Now, what is overfitting? Overfitting is something where the model tries to learn considerably well with a limited set of data, which means my model might not work well outside the data given. The reason being, I have very limited data. 14 records is too small for linear regression to learn. There might be many other patterns which it could have missed because that pattern is not there in the data. So it missed to learn that pattern. So it is always suggested to have as much data as possible, which should capture as much learning as possible, and that would avoid the overfitting of my model. But as of now, I will go with this 14 records, and I consider my model to be good because it is overlapping considerably. Let's try to understand the other parameters. Let's try to plot the error terms. What do I mean by error terms? Error term is y actual minus y predicted. So I plot this value in the same way as I did earlier. I have an index in my x-axis and y test minus y pred in my y-axis. If I notice here, there is no particular pattern which I can find in my error terms. It is quite zigzag. I don't see any pattern, which gives me an indication that there is no learning left in my data. I have covered almost all the learnings. Had there been a pattern in this graph, I would have reconsidered my model and I would have assumed that there is something which my model has not learned yet. As of now, I'm good with this because I don't see any pattern to it. Let's go to the next one. I try to do a distribution plot of the same data, y actual minus y predicted. I can see there is a normal distribution of the error. Now, what do we mean by normal distribution? Normal distribution is the one which concentrates highly on the value of 0 and gradually increases or decreases as it goes, as it goes away from 0. If you see here, the most of the values are concentrating highly on the 0 and it gradually decreases as it moves away from 0. This is called a normal distribution or a Gaussian distribution of error. This again gives me an indication that this could be a good model because my error is concentrating mostly on the 0 part, near to 0 part. Okay, now let's try to understand two more parameters. The one is mean square error and the other one is R square. I can calculate the mean square error and the R2 score by the two methods. This would take the y actual and the y predicted as the parameters. Once I calculate that, I print that and I see my mean square error is close to 25, and the R square is 0.98. Remember, the R square has to be in between 0 and 1, and the higher the R square, the better my model is. 0.98 is indeed a very good value, and 25, the mean square error, is also a good value. So here I can safely assume that my model has done well because the number one, the mean error is less in between the actual and the predicted. Number two, the R square is doing pretty good. All right. The last and the final one, I would like to plot a graph, a scatter plot between the actual y and the predicted y. So predicted y goes in the y-axis, the actual y goes in the x-axis. Once I plot this, I can notice here this forms a nice linear pattern, this which means they are good, they are correlated well with each other and they go hand in hand, which again gives me an indication that this should be a pretty stable model and I can very much settle down with this model as my prediction model for the number of minutes which needs to be taken by a computer technician to fix a given set of computers. Thank you.